Hello, hello. So today we're talking about the counting to infinity problem. Specifically, the question on the table is whether the set n star is countable or not. So there's a lot to unpack here, so let's take it step by step. The first thing we'll talk about is what does it mean for a set to be countable in the first place? So we define a set A to be countable if and only if the cardinality of the set, or the size of the set A, is less than or equal to the cardinality of the naturals. In other words, we say that there exists an injection from the set A onto the naturals. Now, there's nothing too special about n. In fact, you can replace n by any of your favorite countable sets. So you can put any countable set here. And as theoretical computer scientists, one set we really like to use is the set sigma star, which we prove to be countable. So then we just want to create an injection from A onto sigma star, which is the fancy way of saying an encoding. So in fact, we like this method of proving the countability of sets so much that we gave it a cute little name. Specifically, it's the CS method. Awesome. So the next pressing question, I guess, is what is n star and can I eat it? So to answer the second question first, no. But yeah, we've seen something like this before, right? So we've seen L star, which is just a concatenation of a finite number of strings from L. So maybe n star is something similar. It is the concatenation, for whatever that means, of a finite number of numbers from n. So maybe like you take 1, 5, and 251 and you write them close to each other. Now, this is kind of weird, right? So, in fact, what we'll actually do is we'll properly delimit them by using commas and like convert it actually to a tuple. So then what the set n star actually becomes, if you use set builder notation, it looks something like this. It's the set of all tuples of the form x1 to xk, so for k in the naturals, so basically all finite length tuples, where each element within the tuple is actually an element of the naturals. Sweet, I like it so far. And then the final question, to rephrase it again, is whether this set is countable or not. So I encourage you actually to take a couple of minutes and think about this. Maybe venture a guess on whether you think n star is countable or not, and maybe refer yourself to similar applications of the star operator we've seen in the past. And yeah, pause the video, think about it, and then feel free to unpause when you have a few ideas. Okay, so hopefully you thought about this, and maybe you thought about the set sigma star that we have seen before and we know to be countable. Maybe n star is something similar. But then maybe you second guessed yourself and thought that sigma is actually a finite set and n is not finite, so maybe something weird is happening. But we've also seen things like L star before, which is just a language, so it's actually a subset of sigma star. And we also know that that is countable. So, and in fact, we actually made no claims about L being countable or finite initially. So it might actually be the case that n star is also countable. So we'll venture a guess, be ambitious, and try to show that n star is countable. And how we'll do that is, again, by using the CS method. So we'll try and create an encoding scheme for n star. Now, before we do that, let's remind ourselves that the set n is countable. So the CS method tells us that the set n is also encodable. So there exists some reasonable encoding scheme for n. This exists some encoding scheme enc for n. And it has some alphabet. Now, in fact, we know of many encoding schemes for the naturals. You've seen of the binary system, the hexadecimal system. We'll be vanilla here and just go with the good old decimal system. And we'll actually be making use of this encoding for the rest of the problem. But yeah, the goal overall is to actually show that n star is countable. So we actually want to create an enc prime, which is an encoding for n star, and it goes to some sigma star, and maybe I should call this sigma prime for the naturals. And yeah, this time it's going to sigma star. Maybe it is the same sigma, maybe it's not. We'll talk about it. But the overall goal of enc prime is that it has to be, of course, an encoding, so it has to be an injective function, and it has to map elements to a finite length string. And at the end of the day, you would also like it to be a well-defined function. That would be cool. All right, so how do we want to do this? Well, actually, how you would choose to define enc prime will not be very different from what you would actually expect it to be. We have this concatenated tuple of natural numbers, so to encode this, we might as well concatenate their encoding. So you can take enc of x1, and you can follow it by enc of x2, all the way to enc of x sub k. But this goes back to the same problem we had before about not being able to distinguish between where a number ends and a number starts. So what we'll actually do is we'll delimit these encodings by whatever your favorite symbol is. This time I'll use dollar signs. So our sigma here is actually the set 0 through 9 union with this special symbol, which is the dollar sign, which we're using for delimiting. Cool. So hopefully that makes sense. And now we have a claim, and we want to at least argue correctness, or at least convince ourselves that what we are claiming is true. So, well, we won't go into too nitty-gritty about the proofing process because it's pretty straightforward to see that enc prime is actually injective. And the reason for that is if you just spend some time staring at two tuples who have the same encoding, you can pretty straightforwardly reason that actually the tuples must be element-wise equal. Okay. Then what about finite length strings? This should probably be strings. Now observe that k is actually a finite number, and each of these encodings is a finite length encoding. So we are just concatenating a bunch of finite length encodings, and at the end of the day, we get a finite length string. So that's cool. And there's nothing weird going on about one tuple having multiple representations, so we probably won't run into well-definedness issues as well. Of course, this wasn't the most formal argument in the world, but I think without going into too much pedantry, an argument like this covers like the broader ideas of why this enc prime works. Cool. So yeah, if this was convincing, you should be convinced that n star is actually a countable set. To extend this problem a little bit, what if we replace n by, say, some other countable set A? And yeah, you will not be incorrect to notice that not a lot would change about this problem actually. In fact, we will still rely on the encoding of, well, not n, encoding enc of not n, but of our finite set, of our countable set A, its alphabet, and then we will union some delimiting symbol again, and then encode it in a very similar way. So, yeah, for any countable set A, it is pretty easy to see that A star must also be countable, and that's a pretty cool result. Sweet.